We can use some of the same concepts in solving logarithmic equations as we do solving exponential equations. And the first of those is when we have a logarithm equal to another logarithm and the bases of those two logarithms are the same. So just like if we have 2 to the x equals 2 to the 3x plus 1, if we have an equation like that, if the bases are the same, then we can just basically ignore the bases and then set those exponents equal to each other. Well, so too can we do the same thing with logarithms. If we have a logarithm on one side and a logarithm on the other side, and it's the same base, then we can just take those insides and set them equal to each other. So in this case, we could say 5x plus 2 has to equal x plus 14. If these two sides of the equation are going to be the same, then those insides have to be the same so long as the logs are the same. And so we just solve using our regular algebraic techniques. So we get 4x on the left here after subtracting x from both sides, plus 2 equals 14. We can subtract 2 from both sides. We get 4x equals 12. And then dividing by 4, we get x equals 3. Now, one thing we do need to make sure of in these logarithmic equations is to go back and check to make sure that our answer doesn't result in 0 or a negative inside of a logarithm. And in this case, that's clearly not going to happen. If I plug in 3 for x, I'm going to get 17 on the left. If I plug in 3 for x, I'm going to get 17 on the right. We're not taking the log of a negative or a log of 0, so therefore this answer works. In the second example, we've got the same thing. We've got the log base 3 of x plus 3 equals the log base 3 of x squared minus 9. Since we have the same log base on both sides, we can go ahead and just take the insides and set them equal to each other. Now in this case, we have an x squared in our equation, so we're going to have to pile up everything on one side and set it equal to 0. So I'm going to subtract x from both sides, and I'm going to subtract 3 from both sides in order to get everything piled up on one side equals 0 on the other. So we get x squared, and then we have this minus x that we just brought over, and we have minus 9, minus 3, those combine to make minus 12. So now we're going to solve by factoring. So I can break this into two sets of parentheses. I've got x as the first piece in each set of parentheses. We're multiplying to make a negative, so we need one positive and one negative. And so we're looking for a factor pair that multiplies to make 12, but then combines to make negative 1. So we're going to have 4 and 3 are the two numbers that will multiply to make 12, but have a difference of 1. And we need the 4 to be negative, so that when we add together negative 4x and positive 3x, we get the negative x in the middle. So now we take each of those factors and set them equal to 0. And so we get x equals, if we subtract 3 from both sides, we get negative 3. And then over here, if we add 4 to both sides, we get positive 4. And so now we need to go back and make sure that neither of these results, answers results in either 0 inside of a logarithm or a negative inside of the logarithm. So if we check negative 3 plus 3 equals 0. So that means we would be taking the log of 0, which is no bueno. Same thing here. If I plug in negative 3 for x, negative 3 squared is positive 9, minus 9 is 0. So I'm going to have to toss out that negative 3 answer, but our answer of 4 is not going to be problematic. 4 plus 3 is 7, 4 squared is 16, minus 9 is 7. So our only answer that we're going to keep in this case is x equals 4. So it's very important that we go and check our answers, especially in circumstances where we have multiple answers that we obtain from our quadratic techniques. A lot of times one or even both of those answers might get thrown away. So problems that just have a single logarithm, like what we see in the two examples here, where we have a 4 times a log base 4 of 2x equals 16, or on the second example, same thing. We have a single logarithm equaling some number on the other side. We're going to have to rewrite these as exponentials. And so our pattern for that, if we go back to our original rule for rewriting logs as exponentials, so log base b of y equals x can be rewritten as b to the x equals y. So the base of our logarithm becomes the base of our exponential. What the logarithm equals becomes the exponent, and then the input into the logarithm becomes isolated on the other side. So that's how we're going to get this x out from inside of the logarithm. But before we can do any of this rewriting, we have to isolate the logarithm. So in this case, I have this 4 that's multiplying the log, so I'm going to have to divide both sides of this equation by 4. So that'll eliminate this 4 out front, and so that gives us log base 4 of 2x equals 16 divided by 4 is 4. And so now with the logarithm isolated, we can use our pattern here to rewrite it as an exponential. So the base of my logarithm becomes the base of my exponential. What my logarithm equals is my exponent, and then that's going to equal the input into the logarithm, which is 2x. So now 4 to the 4th power, I can either do that on my calculator, or 4 times 4 is 16, times 4 is 64, times 4 one more time is 256. So we get 256 equals 2x. So then we just have to divide by 2, and so we get x equals 128. And if we go back and check, we can see that plugging in 128 in for x isn't going to be problematic. We're not going to be taking the log of 0 or a negative, so we have confidence that that answer is just fine. In the second example, we don't have to do any work to isolate the logarithm, so we can just right away move to rewriting it. So the base of my logarithm becomes the base of my exponential. What the logarithm equals is an exponent, so that's going to go over here as the exponent on the 9, and then we're going to set that equal to the input into the logarithm, which is 6x. So now we're in the same place as we were on the previous question. We've got 9 to the second is 81 equals 6x. And so then our last step is to divide both sides by 6. And so we get x equals 81 over 6, which we can reduce. Both the top and bottom can be divided by 3. And so if we do that, 6 divided by 3 is 2. 81 divided by 3 is 27. So we can go ahead and leave our answer as 27 over 2. And so if we take a look at our original problem, we're again not going to have any issues with log of 0 or log of a negative, so we're confident that that answer is correct. Our next example has just a single logarithm, so I'm going to first have to isolate that logarithm by dividing both sides by 6. Before I can rewrite it in exponential form, I have to isolate that logarithm. So now I have natural log, so ln of x plus 4 equals 18 divided by 6 is 3. So now that we have that logarithm isolated, we can use our pattern to rewrite it as an exponential to get that x out from inside of the logarithm. Now recall that natural log is log base e. So even though we never write it like this, that's the base of that logarithm. And so seeing it like this may make it easier for us to rewrite it as an exponential. So the base of our log is the base of our exponential. The logarithm is an exponent, so that becomes the exponent. So we have e to the third equals, and then that's going to equal the input into the logarithm, which is x plus 4. And so now, to solve for x, we're going to have to subtract 4 from both sides. So we end up with e to the third minus 4 equals x. So sometimes, similar to when we're solving problems involving circles and pi, we'll be asked to leave our answer in terms of e rather than pushing buttons on a calculator. So this would potentially be an acceptable answer, but if we wanted to calculate it out, we would just have to use the e button on our calculator. So using our calculator, e raised to the third power is going to be, if we round to the nearest thousandth, 20.086, and then we still have the minus 4 there, so then we can subtract 4, and so we end up with 16.086 as an answer. And again, if we check, plugging in a number a little bit larger than 16 isn't going to be a problem for us, so we've got a correct result. Our last example is a little bit different than the others because we have two logarithms that are being added together to equal just a regular number. So before we can rewrite it as an exponential, we have to combine these two logarithms into a single logarithm, then we can rewrite it. And the way we're going to do that is by using our log properties. If we recall, if we're adding two logs of the same base, then I can rewrite it as a single logarithm where I'm multiplying the two insides. And so in this case, it's going to be x times x minus 6. So I'm going to multiply those inputs inside of a single logarithm. We're not going to add those inputs, we're going to multiply them. The sum of two logs means you can rewrite it as a single log with the product of the two inputs. And then that's still going to equal 2. So now we're ready, since we have it down to a single logarithm, to rewrite it in exponential form. So the base of our log becomes the base of our exponential. A logarithm is an exponent, so that becomes our exponent, 4 to the second, equals the input into the logarithm, x times x minus 6. So now we're ready to start solving this equation. So 4 squared is 16 equals, on this side I'll go ahead and distribute, and I get x squared minus 6x. We have an x squared in our equation, so we're going to have to solve by factoring. In order to factor, we have to have it equal 0. So I'm going to subtract 16 from both sides. So I get 0 equals x squared minus 6x minus 16. And so now I can break it up into my two sets of parentheses. So I know the first piece in each set of parentheses is going to be an x. I'm multiplying to make a negative, so I need one of each. And as we think about the factor pairs that multiply to make 16, 4 and 4 isn't going to do it, but 8 times 2 will. So we need a negative 8 and a positive 2, so that when we combine the negative 8x plus 2x, we end up with that negative 6x. So once we have it factored, we can set our factors equal to 0. And so then on this side, we'll subtract 2 and get x equals negative 2. And then on the other side, we'll add 8. And so we get x equals 8 as our second answer. And then, of course, as we have on all these log equations, we need to double check to make sure that our answer does indeed work in the original problem. And so we can see that negative 2 is going to be problematic, because if I plug in negative 2 into these two logarithms, I'm going to be taking the log of a negative number. Log base 4 of negative 2, or over here we're going to end up with log base 4 of negative 8. So I have to throw that answer out. It doesn't work, but I do have an answer that does work. 8, if I plug that in, we don't have a problem with either of those logs. So our only answer on this one is going to be x equals 8. So in this problem, we had to use our log properties to combine the two logarithms into a single log before we could rewrite it as an exponential.